hear me?
Yeah, we can
right
hear
here.
you fine. So without any more further ado, I'm going to leave it to our first presenter of the day, Sandra Bitter. Thank you, Sandra, for talking to us.
So good morning, everyone. So let me start by saying I'm very sorry I cannot be there in person, but using a video connection seems a good way for me to participate in the workshop. I've been following yesterday's talks, and yeah, so just a bit about myself. So not every one of you may know me. So I'm Sander van der Hoog. I'm currently head of simulation at lucidminds.ai, which is a startup in Amsterdam. That's mostly focused on ABM and data science projects. And we're also very interested in bringing together research and academia with policymakers. So I'm working also with people at the ECB, for example. And other than that, Lucid Minds basically functions as an expert hub. So in the sense that we have a large network of partnerships with other startups in different areas, such as satellite imaging, for instance. Or other data science companies. I myself, I'm involved as an agent-based modeling expert, and we also have people working on smart contracts, data privacy, and algorithmic transparency. So these are things that in the European context, the European Commission finds very important. So we're kind of jumping into that niche market. Now, regarding the topic of the workshop, inverse generative models, I am not yet very involved in this, I must say, but there might be some links to the projects I'm currently doing. So the two projects in particular I'm currently involved in. The first is a project on the housing market in the Euro area. So this is with colleagues at the European Central Bank and at the IMF. And this project has a strong focus on macroprudential policy and systemic risk. So relating to the housing market in particular. And project number 2 is on empirical validation of large-scale ABMs, which I am doing together with Sylvain Barthes of University of Kent. So I will tell a bit about the second project. And this is perhaps more related to the topic of inverse generative social science. At least there is some use of surrogate modeling and machine learning techniques. But it is also related to the first project in a sense, because of course, in the end, we want to estimate a large-scale macroeconomic housing market ABM on empirical data from the Euro area. And so the purpose of this project is to come up with a generic method to estimate such large-scale ABMs. So the idea is the following. So the setting, basically. So suppose in our case, we have a macroeconomic ABM. And suppose you only have access to the time series data that is generated by that simulation model. And you can generate any amount of such simulated data for any parameter setting in principle. But the large-scale ABM is computationally heavy to simulate. So imagine one run of 1,000 iterations takes about 30 minutes on one CPU core. So then there is a limited amount of data that you can generate given some computational budgets. So this particular problem is not just a problem for agent-based economic models. It's known in operations research as costly simulation experiments. And it is also known in medicine, for example, if one experiment costs several weeks to complete. So that is the basic problem we are trying to solve. So this is kind of an illustration of some time series you get out of a macroeconomic model. So these are typical macroeconomic variables that we would look at. So first you have the output of the total of the economy as a whole, just in units. Then you have something like capacity utilization of the production capacity, and this converges to 70%. It's kind of a normal value. Then you have an ECB interest rate, so policy rate, which is around 2%. And then you have several things which are kind of showing exponential growth, like GDP, consumption. These are all growing with about 2%. And the unemployment rate on the bottom left around 10%. So this is kind of eyeballing if the system is doing something that's okay after some initial transient period. But of course, we want to do something a bit more rigorous than this. So what we're actually doing, so the problem, how we see it, is as follows. So the problem of parameter calibration in general, you could say you can reduce it to the problem of finding the smallest distance between two distributions. Given a model M, and some empirical data series. You want to find the set of parameter calibrations theta such that the distribution of output of the model M given theta is as close as possible to the distribution of output given the data. And so there are two distributions here, the distribution of output from the model and the distribution of output in the empirical data series. And the objective is to minimize the distance between the two. But it is not entirely clear what as close as possible means. So there are different ways to measure this. And it is also not clear what space to, in what space to measure this. So there's a problem about defining a space and defining a metric on that space. And so if you look at the literature, there are basically two approaches. So the first approach is called in-the-loop simulation, which I will call exploration of the parameter space. So this uses a continuous space of model calibrations omega, and then some mechanism to explore this space omega with some search algorithm that possibly uses some gradient methods. Doesn't have to be a gradient method, can also be gradient free, of course, but that's usually how it is done. And then you adapt the parameter calibration iteratively, and you stop when you are no longer making any progress. So that's the first method. The second method I would call no in the loop simulation. So that could be referred to as exploitation of the parameter space. Then you start with a discrete space with pre-specified number of model calibrations, let's call it gamma. And then you exploit gamma for all these pre-specified parameter calibrations to the best you can. And so here what you would create is a sort of input-output response function. You would create a fitness landscape where the input to this mechanism is the parameters, and the output is whatever metric you have on this distribution of the output of the model. And then you want to, of course, find a minimum on this response function. And yeah, that's basically the method we are using, because we have these computationally heavy ABMs, and many of these in-the-loop estimation routines where you would iterate over the parameter space are then prohibitive, because due to the computational budget, you cannot do these iterations. So what we actually do is as follows. So Sylvain in previous papers developed a criterion called the Markov information criterion, called MIC for short. And the MIC is essentially a measure for a pseudo log likelihood score. And we use it to calibrate this Euroset Unibi model, which is this macroeconomic agent-based model. So it's not a Bayesian estimation method, but instead it is based on information theoretic criterion, and using a measure of the cross entropy as the pseudo log likelihood. And then you want to minimize this score over a pre-generated set of data. Now the idea of the Markov information criterion is based on the Kullback-Leibler divergence, which is basically distance between two random distributions. And to recall, in the equation there on the right-hand side, the KL divergence originally is a measure for the inefficiency of a compression algorithm that is based on the probability of some model of the data. So it is a measure of inefficiency, and therefore we can use it in that sense to compare models. And the Shannon entropy, which is in the middle, first term on the right-hand side, is just the negative logarithm of the probability mass function. So here we write 1 over the probability mass function, but you understand it can be a minus in front of the logarithm. So using the expectations given the true probabilities of the data generating process, the DGP. Now, if we would know this data generating process of the real world data, then we could of course use these true probabilities in the compression algorithm. And then we would achieve optimal compression of the data, and this cross entropy on the left would be equal to the Shannon entropy on the right, and this KL divergence would be 0. But unfortunately, of course, we don't have these real probabilities, because then it would mean that we have found the perfect model. So in general, this KL divergence will be positive. And now we can use this as our metric for getting the distribution of our simulation data as close as possible to the distribution of empirical data. That was already shown by IGSS that you can basically use this by taking differences. So if you take differences between the cross entropies, then the Shannon entropy is constant for all models. So that falls out, and you basically have the difference between these KL divergence terms between two different models, I and J. Now, the only difference that the assumption that we are making is that the process that we're looking at is a Markov process. It doesn't have to be a one state, one period Markov process. It can be an n period Markov process. But so that's the move from the IGSS information criterion to the Markov information criterion, that we are assuming that these are Markov processes. And then the trick is basically to look at these differences between cross entropies and using the probabilities of the model or time series of the model to find the distance to the empirical data distribution. So the roadmap basically that we are following is as follows. So the entire estimation routine is a couple of steps. We start with an experimental design that has to cover the parameter space sufficiently well already from the outset before we do any simulations. So the idea is that the model generated outputs are then sufficiently informative for this MIC measurement to have discriminatory power to do some model selection. And we call this model selection parameter calibration here because we're looking in the space of parameter samples. And this would be possible purely on the basis of the time series output. So without any knowledge of the mechanisms of the data generating process or the model. Then we simulate for these set parameter samples, we simulate the model. We divide it into a training set and to and a validation set. And then we run step 2, which is the probabilistic modeling. So we try to extract from the simulated data the conditional probability structure. So you could say the Markov transition probabilities in the simulated data. And we are trying to create a compression algorithm using these probabilities. So this step 2 uses binary trees and the compression algorithm. And we use here an existing method, which is this context tree weighting, which is creating this binary tree. So that's basically mapping the time series data into probability space. And then the MIC measurement measures the contribution of a single observation in a time series to an overall cross entropy as compared to the empirical time series. And then we average over those measurements across a time series. So we get a pseudo log likelihood score for that particular parameter setting, which is this MIC score. And that creates a model response surface of the model in terms of these MIC values. And this will be our fitness landscape to minimize over. And then step 3 will be that we use this landscape and apply a surrogate modeling technique to interpolate this landscape. And for this, we use stochastic kriging to do this interpolation. And then we minimize this interpolated response surface in order to get new candidates, new possible best calibration settings that minimize this distance between the distribution of model output and the distribution of empirical data. So that's the roadmap. So I'll just show you each stage in a bit more detail. So for stage 1, where we have this experimental design, we want a discrete sample space, and here you see an example of 8 parameters. So we have a matrix here which gives you the 2-dimensional projections of each pair of parameters. That's why on the diagonal there is this diagonal. So this is a set of 513 samples. So that's one sample in the center and then 512 points around it. So it's a power of 2. And for this, we use nearly orthogonal Latin hypercube sampling to obtain this initial sample. And then for each of these parameter combinations, so these 8 vectors, we do 1,000 Monte Carlo replications for each parameter setting with a different random seed. And then, of course, since, well, originally the model was 15 minutes to do one run, and then we increased the length of these runs. So now we're using 30 minutes. And so then, of course, we use a distributed computing environment to generate all the data for these samples. And then comes the next step. So then we have the pre-generated data. So then we're going to use this for this probabilistic modeling and encoding. And for this, we use a binary discretization of the real value time series into several levels. And we encode this into a binary tree where we basically count if from a previous level in one time series, if you are going to one of the other levels, and then you are in a branch and you just add the number on this branch. So that's basically just counting in a time series. You scan all these time series, and you end up for one parameter setting with one tree with basically numbers on it, and then you can take ratios, and those are basically probabilities for this particular time series. So very simple counting method. So that's this context tree weighting. And then we encode it with the binary encoding, and for that we use a binary string encoder, which is also off the shelf. And so that basically encodes this Markov transition matrices, or the probabilities of those. And that gives us this, this compression algorithm. And then we use these binary trees per parameter setting to compress the empirical data and measure how efficient that is. So the mix score is then basically measuring this cross entropy of this compression. So how good is this mix score, or how good is this particular model in compressing the empirical data? And then we can compare pairs of models. So that's the next step. So we have these measurements from this, the mix measurements from these trees. And then we construct this model response function. So that's this third step where we have, first of all, these black dots. So these are the discrete measurements, 513 of them. This, by the way, is just an illustration of how that looks, because the surface here, of course, the floor is two-dimensional, and you would have to imagine an 8-dimensional space at the bottom, and then a univariate metric, which is this MIC value. So we have these 513 black dots, and then we interpolate this with stochastic rigging, and then we create this surface. And given this surface, we can, of course, look again for minima in this surface. And then we have new candidate parameter calibrations to test. So how does this work? So the global optimum would be a best fitting model, but of course, we assume that this measurement is also a noisy measurement. So there is some noise around this surface. So therefore, there can be points which are close together, which are not statistically distinguishable. And for this, we use a concept which is due to Hansen, which is a model confidence set. It's kind of like a confidence interval in the model space. And so we can have a little set of model parameter settings which are all equally good performing. So an example of some results are here. Here we have two parameters. On the vertical axis, you see OECD countries, 32 OECD countries, including the euro area. And we get parameter estimates for each country. Now the blue dots here represents high scoring initial sample points. So these cannot be distinguished from a statistical point of view. And then the crosses, so the blue crosses are the absolute best performing parameter values. Then the red points, those are these new candidates which we get after kriging. So these are new optima of this interpolated space. And there were 175 of them. So that's on average per country, it's 6 new samples, which we wanted to try. And for those, of course, we had to regenerate new data because they were not in the original sample. So we did basically one iteration of this kind of search algorithm after we did 513. Now, on the left side, you see that there is some alignment of these blue crosses on one value. So that indicates that this parameter gamma, which we're looking at, is kind of a generic parameter that works well for all these countries for one particular value. But on the right, you see this is not the case. We have two vertical lines, which are basically two values, which are, yeah, you can basically say you can classify these countries into either having a low value of parameter D or a high value. Yeah, so this is kind of a first proof of principle of this kind of method. So as a result, you can see you can identify some parameterizations which are different among different countries. So to summarize this, basically what I've shown is a three-step method. So we start with an idea of exploration versus exploitation of the parameter space. Then we have an initial sampling technique with a fixed parameter, a discrete parameter space. Then we use a model response methodology to do this interpolation. And we use a surrogate modeling for that, this stochastic rigging. And we end up with some parameter estimations where we can say, okay, we are at least more rigorous than what we would do when we were eyeballing a lot of time series data. So that's basically it. Here are some references, some papers of the model and of this method. And then I thank you very much, and I will look forward to some questions.
This one right there. Robin has one of it.
Thanks for a fabulous talk. I really enjoyed that. One question I had would be, what do you perceive as the benefits of going through the kind of Markov modeling steps compared to just looking at some more conventional time series error term, like mean square error across the data points? Is there do you see particular advantages? Did you compare it to a more conventional technique?
So one of the things that's interesting in this literature on say trying to estimate agent-based models is that, of course, we first try the existing techniques, and usually Bayesian techniques or approximate Bayesian computation, things like this. And usually the problem there is which metric to choose, right? If you do like a simulated method of moments, the question is which moments? First moment, second moment only, or do you go to 10 moments? Similar would be with mean squared error. So first question is in what space? And so if you just take time series and you take differences between time series, there are, for example, there is a method by Francesco Limperti in Pisa who is constructing a var. So he uses time series, then constructs a var, and then for different models compares the parameters of this var. That's also possible, of course. The different approaches currently in the literature. And one thing which we are wanting to do for a long time now is to basically do horse races. So to basically confront the different models with different methods and see which method works better on which sort of model. That's kind of outstanding still, this kind of idea. Because it's also clear that there is not one model or one method which works for all models. But so for us, the most generic seems to be, okay, the Markov property in some time lag, and then use this kind of idea of information criteria.
Thank you, that's great.
Have you considered using evolutionary methods to explore the landscapes?
Well, so the evolutionary method would be an in-the-loop simulation technique, I would say. It would be kind of just iteratively exploring. And then I would be interested to know if you would have a system where it takes like 30 minutes to get one observation, if there is such an efficient technique for that. I mean, from the start when we were thinking about this, okay, we can do such things, but it seems like it's then going too slow, and we would have a too high computational load to do such things.
The key there is to not just do naive evolutionary exploration, but rather do gradient mapping as you go, and use increasing information about the gradient space as you're exploring to optimize where your next step is. So there's a considerable literature on that kind of gradient space knowledge optimized evolutionary exploration, which is just right for this kind of simulator in the loop kinds of problems where the runtime on the simulator is high.
Okay. Yes. So I think there are some people doing that with kind of financial market ABMs, but I think in the realm of macroeconomic ABMs, nobody has done that so far.
Yeah, I was involved with a company that did it with respect to computer chip design by machine, and it was very, very high dimensional space, basically the number of components on the circuit, and we were able to get good results with only 1,000 explorations, while one would need tens of millions if one just did naive evolution. So I'd say it's worth looking at if you have any interest in another approach.
Yes, sure. We'd be happy to look at that.
Josh.
Hi, Sander. Thanks for joining us. And yeah, wonderful talk and very interesting and deep work. I'm wondering, have you thought about, or maybe you think it already does, instead of numerical parameters, have you thought of adapting the technique to explore variations in rules themselves?
So which rules do you refer to?
Agent-based modeling rules, if I see a green thing, go eat it, this sort of rule.
Okay, so this, okay, so this would be not in the parameter space, but more in the space of mechanisms, or say different modules of an ABM. So we would have like switches that switching on or off certain behavior rules, or there would be some evolutionary rules inside of the model, if I understand you correctly. So no, this kind of, I would say more advanced technology we have not tried. In our case, we basically have C code, which we compile, that's the model, and we have some XML code which comes in, which tells us the parameters. So the structure of the model is completely fixed in that sense. But certainly an interesting endeavor. I would find it very interesting to work together on such a thing. I have not done that.
Great. That sounds wonderful. I have some thoughts on how you might go about that. So I'd look forward to talking.
Okay.
Thank you.
Yeah, I think that's really interesting. You have the same problem of closeness of rules, don't you? That we're talking about, yeah. Because you have to be able to move on that surface in the rule space. So you still have that same fundamental problem we have to figure out. Exactly, yeah.
So that was very interesting, Sander, and it actually reminds me a lot of the work that Forrest Stonedall and I did back with some of the behavior space stuff and behavior search work that we were doing on NetLogo. But we actually, and one of the things we did when we were working on that, we published this paper called When Do Models Match the Real World, or something like that. And one of the things we found in that was that the error function that you use can vastly change this kind of model response surface quite a bit. So depending upon how you're training the model, right, you wind up getting different sets of parameters that wind up having different effects on the actual model validation. And so we looked at everything from like kind of a root mean squared error to just looking at a correlation, right, to looking at like a Manhattan distance. And I'm kind of curious if you've found in your results anything similar, where I think you're using this information criterion measure as your error measure, right? And if you've tried other error measures and if that's had any effect on the results.
So this kind of coming back to the basics of this design of this MIC measure. So there are some diagnostics in that. So that's kind of 2 papers before this paper. That's kind of the development of this this measure. So that's the first step. This MIC measurement itself is noisy. That's also the reason why we are using stochastic kriging and not discrete kriging in this surface. And of course, there in that stochastic kriging, you also set some process for this noise. And there, I think it is just Gaussian, comes very close to Gaussian processes as well. So if I'm not mistaken, there have been some kind of tests for this MIC measure to see if you use different processes of noise, does it affect the measurement? It does, but of course, then you want to kind of pick a process which is not too distorting. Yeah, so I would refer to those technical papers, basically the papers of Sylvain Bart before this paper.
Okay, cool. I'll take a look.
Hi, Sandra. This is Rob Extel.
Hi.
There was a conference in Leiden this summer about so-called Gaussian process simulator ways to do reduced representation of ABMs, large-scale ABMs, and many of the things that you were using, many of your modules seem to have a lot in common with that Gaussian process simulator approach. Now, have you compared what you're doing to that, or do you know much about that procedure from computational statistics? Apparently, it's a standard way to build reduced form models.
Yeah, so I have been looking a bit into that. I haven't been applying it to this model. So there's 2 things here, I think. So people use these kind of meta models or surrogate modeling techniques to directly make a meta model of the agent-based simulation, which of course is not what we do here. That would be just using it directly on the time series. And what we do here is kind of a bit higher up. You know, we have a step in between, which is this metric. And then we do it on the space of metrics. So we basically only use it for this interpolation. So if we use Gaussian processes here, it would just be a different method to do this interpolation of the surface. You know, some people who've tried, I mean, Thomas Lux, I think, has tried this Gaussian processes on a financial market ABM. So I'm a bit critical of this because it means you're kind of distorting the ABM. You're making a model of this model, but you're not letting it produce kind of this metrics, this distance metrics like we are doing here. But yeah, I want to look into that in more detail. Yeah.
So we should probably move on to the next talk at this point. So thank you very much, Sandra, for your presentation.
You're welcome.